Hello everyone. So we have been talking about quantum cryptography in the last video, and I hope it was clear to you that when we gave the general idea of what quantum cryptography means, and today we will go into a little bit more details and work on something called one-time pad, and then try to understand why do we need a quantum key distribution protocol. All right, so let's try to understand that. So for that, uh, let's first say that there is Alice and Bob as usual, and Alice has a bit string M. Okay, she has a bit string M. Okay, these are classical bits. Please remember that. These are classical bits, and we just want to send a message, nothing else. Okay, so of length n. All right, and what she does is that she generates uh, a secret. Okay, give a secret private key k. Okay, which is of length n as well. Okay, so the thing to notice here is that I have a message which is of length n, and my secret key which I generates randomly. So let me use the word to be more specific, that randomly. Okay, so now it is a random secret it's a random secret private key. Okay, so all the bits in this key is also is random. Okay, that is what is meant. These are also classical bits. All right, there's nothing quantum yet. So what Alice does is that she encrypts her message. So she had M, and what you can do is that you can perform a sum modulo 2, or you can call it addition modulo 2, or you can call it the XOR operation, right? If you check the truth table of the XOR operation, it is the same as sum modulo 2. All right, so I will call it XOR from now. So what you do is what Alice does is that she does this sum modulo 2 or XOR operation bitwise. So what does it mean? That both of them are of length n, so you can add each bit bitwise. So for example, let's say the message was 101 and your quantum key was 110. So what do? You do a sum modulo 2. So this is a 1 here, this is a 1 here, and this is a 0 here. Okay, so this was your M, let's say this was your key, and then this was your C. We call it this C. Okay, so the thing to notice here is that as this key was random, each bit of this key was random, this message, if even someone in the middle checks this message, there is no way he or she can predict what was M, right? Because XOR operations are not one-to-one. All right, so there is no way if you don't know the private key, you cannot have any idea about M. Okay, if you just look at C, you cannot say anything about it. So that is how Alice encrypts her message. So she sends C to Bob. C is sent to Bob. Okay, then what does Bob do? Now Bob had the key, the private key K from before. Okay, so what he does is that he receives this C and does the same XOR operation on the encrypted message C. And what is it? This is nothing but M XOR K XOR K, right? So now you can see that K plus K would just give you 0. Why? Because 0 XOR 0 would give you 0, and 1 XOR 1 would also give you 0. So what you can say is that this is nothing but M XOR 0, then this is nothing but M. So you can see that Bob has retrieved the message M that was sent by Alice. But what they used is that they had to share a secret key K, which was of the same size of the message M. All right. So if and this has but what there are some catches. All right. Alice can only use this key once. Why? Because let's say that Alice wants to send a message M1, and what she does is that she uses an encrypted version and sends C1, and there is an eavesdropper who can read C1. Similarly, there is another message C2 which is nothing but M2 plus K, because she's using the same encryption key. So now what happens is that if the eavesdropper tries to add these two encrypted messages, I mean by adding I mean that performs an XOR operation, then what he or she reads is nothing but M XOR M1 XOR M2. All right, because K XOR K would give you 0, and that is nothing but this is the same as M1 plus M2. All right, so the eavesdropper, when it is used twice, can extract some message about both M1 and M2, which was, there's no encryption key inside now. All right, and if there is a third message, then the eavesdropper can also know about the key as well. So what is the solution? So we need to generate a key. We need a key for, okay, let me be more precise. We need a unique key for every message. All right, and how can we do that? One possibility is they have to share it via a public channel, but this is the key and we want to keep the message private, so we cannot share the encryption key in the public channel. Secondly, there can be some trusted intermediate medium, but there are loopholes as well. We want a more secure version where there's no loophole at all. So the solution to that is that we will distribute the key via a quantum channel. Okay, this is the most important message in this video, that the distribution key will be the encryption key will be distributed via a quantum channel. Okay, and once it is distributed among Alice and Bob, then they can encrypt their message and send it via a public channel. That's not a problem. So your messages will be sent via a public channel, but the key, which we denoted by K, and which we will use to encrypt the messages, will be shared via a quantum channel. All right, and there are many quantum algorithms which does it, which can share quantum key between two parties using a quantum channel. And some of the examples are, one is BB84, which uses 4 qubits. That includes non-orthogonal pairs. Sorry, non-orthogonal pairs. Okay, then there is other one, which is B92, which uses 2 qubits. Okay, which uses 2 non-orthogonal qubits. And then 3 is E91, which uses an entangled pair. Okay, which uses an entangled pair. So we won't have time to discuss all of this. So we will discuss the first one, which is the BB84, which includes 4 qubits, and this is one of the first quantum key distribution protocols ever discovered, and we will talk about it in great details in the upcoming videos. All right, I hope this is clear to you. The idea is the messages will be encrypted by a key, but the encrypted messages will be sent through public channels. That's not a problem, because if there's an eavesdropper, there is no way for him or her to find out what the message is. But the main idea is that the key will be distributed via a quantum channel, and that is not that is a private channel. And we will show that even if there are eavesdroppers, we can make it extremely secured. All right, so I hope this is clear to you, and we will talk about the BB84 quantum key distribution protocol in great details from the next video. Thank you so much.